In this video, we're going to look at writing the formulas for ionic compounds and naming them. There are a few different rules that we need to follow when we name ionic compounds. And the first one is that when we write the formulas for these ionic compounds, we're going to use an empirical formula. What that means is we're going to focus on the ratios of these elements to each other instead of the exact number of elements that are there. For example, when we looked at sodium chloride in the last video, I could have a whole lattice structure full of NaCl where they're all connected together, where they're all nearby each other. But I'm not going to write the formula Na4Cl4 because when I really have a brick of sodium, I might have millions of sodium molecules and millions of chlorine molecules. I might have Na 6 million. And I don't want to write Cl 6 million. This is a ridiculous amount. So we just take the ratio between these two. And for sodium and chlorine, it's just 1 to 1. NaCl is 1 to 1. When we have ones in a chemical formula, we just don't write them. We're going to write 2s, 3s, 4s, 5s, but if it's just a 1, it's implied because if it wasn't a 1, I wouldn't write it. If it was a 0, I wouldn't write it. I don't need to write a carbon 0 here. We know carbon's not there because I didn't write it. Okay? So when we're crafting these formulas, how do we know how many there are? How many of each? Well, the way ions are going to get together is going to be in a way that balances their official charges, their ionic charges. And so when I look at something like sodium and chlorine, I look at this and I see that both of them have a charge of 1. Sodium is a +1, chlorine is a -1. And so it's going to be NaCl, right? But now if I look at sodium and oxygen, well, oxygen's got a charge of -2. I need that plus and that 2 minus to balance out to 0. So how can I balance that out to 0? Well, the way I do that is I just bring another positive charge. So I've got a total of 2 positives here and a total of 2 negatives here, and that balances out to 0. And so when I put sodium and oxygen together, I'm going to get Na, and I'm going to bring 2 sodiums for every 1 oxygen. Now what about this right here? This is carbonate. This is called a polyatomic anion because it's really, carbonate is carbon and 3 oxygens that have a covalent bond, and the whole atom has a -2 charge. The whole molecule has a -2 charge. And so sodium and carbonate are going to get together, and I'm going to have 2 sodiums for every single carbonate. And so what about this one? This is a phosphate anion. How is the phosphate going to bond with the sodium? Well, again, the sodium has a +1 charge, and so I'm going to need to bring 3 +1s to balance out that 1 -3. So it's going to be Na3 and then PO4. This 4 right here, this is part of the phosphate ion. A phosphate ion is really going to be looking like this. It's going to be all 4 of these connected together. It's going to take those everywhere it goes. So I don't need to worry about this 4 here. I'm going to keep that as part of this PO4. The PO4 is a whole thing unto itself. Okay? Now what if I increase the positive charge here? What about calcium 2+? Well, now I've got a positive 2 charge, and if I go with chlorine, I need to balance that out with 2 chlorines. So I'd have CaCl2. Calcium and oxygen, well, Ca is a 2+, oxygen is a 2-, so that balances out. 2- cancels out 2+. So we get Ca. Oh, that's straightforward. But what about, it's going to work the same way with the CO3, so let's just skip over to the PO4. What am I going to do here? I've got a Ca2+ and a PO4 3-. How are those going to balance out? Well, if I've got 2+ versus 3-, I need this to balance out to 0. So first off, let's bring another 2+. So I'm going to bring 2 calciums. Now I've got a total of 4 over here and a total of 3 over here. So clearly this needs to go up again. So I'm going to bring another PO4. And that's going to make this 6. Well, now I need to bring another 2+. That's going to make this 6. So now we have this balancing out with 3 calciums and 2 phosphates. Okay? But is there a quicker way than writing all of that out? Well, there is. So I've got Ca3, PO4, and when I have these polyatomic anions, I put them in parentheses, and then write the number of polyatomic anions I have. So the quicker way to do this is, notice the calcium here, this had a +2 charge, and the PO4 here had a -3 charge. And so I'm able to take that -3, and that tells me whatever I use, I'm going to need to bring 3 of that thing, right? See that? And then this +2 tells me over here, I'm going to need to bring 2. So we're able to match those across our 2 ions. And that can give us a very quick way to figure out how many of each should there be. So let's try that again with aluminum oxide. Aluminum is 3+, so how many oxygens do I need to bring? Well, I've got this 3 here, so that means I'm going to need to bring 3 oxygens. And I've got this 2 here, so that means I'm going to need to bring 2 aluminums. So I bring Al2O3, and that's going to be my aluminum oxide. Now we could track those charges. Aluminum has that 3+ charge. Well, 3 times 2 is going to be 6. Oxygen has a 2- charge. 2 times 3 is 6. So those balance out. So we can prove that mathematically. So next I'm going to come down here, and I'm going to look at iron and iron. Some atoms, especially metals, post-transition metals and transition metals, can have multiple charges. They have multiple points where they can be stable. So iron is able to make a +2 cation or a +3 cation. And when it does that, we label it in 2 different ways. Where everything else here, this aluminum, this calcium, this sodium, we just call it sodium, calcium, and aluminum. This iron, when we name this, we call it iron 2. That 2 is reminiscent of that +2 charge. And this we name iron 3. And that tells us it's got a +3 charge. And we're going to do this for all of the cations that have multiple charges. And it is only cations that are going to have multiple charges. So you've got my iron right here, that could have a +2 or a +3. You've got tin over here, that could have a +2 or a +4. So I would call this tin 2 or tin 4. I've got nickel here, I could call this nickel 2 or nickel 3. So nickel 3 would be the nickel, that would be the Ni3+. So we identify that using those names, okay? So that should be pretty straightforward. So when we put the empirical formula together, it's still going to work the same way. We just need to be aware of, is this a +2 or a +3? It's not always going to be the same. And so if I've got iron 2 bonding with oxygen, if I make iron 2 oxide, I'm going to have FeO. Because that +2 balances out oxygens, let's put it right here, oxygens -2. Or if I have iron 3, well, that 3 is going to go to the oxygen. That 2 from the oxygen is going to go to the iron. So I'm going to have Fe2O3. So this would be iron 3 oxide. This would be iron 2 oxide. And that's exactly how I'm going to name these. When I name these ions, I'm just going to take the name of my cation, so the name of my cation, plus the name of my anion, and I'm just going to put them together. So up here I had sodium phosphate, so that was sodium and phosphate, so I just call it sodium phosphate. Okay? And we do have a reference sheet for all of the names of all of the anions, so that should help us put those together. There is one important thing to note, though. When we have monoatomic anions, these anions that only have one atom in them, like chlorine here and fluorine, we replace the INE name with IDE. So this becomes fluoride, chloride, bromide, iodide, so on and so forth. So let's add that in. So when I've got this NaCl up here, this is sodium chloride. CaCl2, this is calcium. Calcium chloride. Okay? And so the easiest way to start naming these is to start looking at a reference sheet and going, okay, what do I have? This is my second name. What am I going to call this? So if I look at my reference sheet, I see oxygen 2-, that's going to be oxide. Great. And whatever I'm bonding that with, if I'm bonding it with an iron 2, then this whole name becomes iron 2 oxide. So this naming can be pretty straightforward. We just need to make sure that when we have these multiple ions, these multiple possibilities. But we are identifying that with those Roman numerals, what the charge is on those ions. Because otherwise, if I just have iron chloride, well, there's two substances called iron chloride, and they have vastly different properties. One is extremely reactive, it's a bright green. One isn't. It's a great drying substance. It'll just pull water right out of the air, and it's a kind of a mustard brown. So they're two distinct compounds that have distinct properties. So we need to make sure that we're identifying those Roman numerals in our names. So what if I'm given a name and I need to create a formula? Well, that can be a little more challenging because I'm going to have to figure out the charges on these different compounds. That's going to be my first step. So I look at my copper 2. So I've got this copper 2. Well, that's going to be Cu for copper, and then it tells me what that charge is going to be, 2+. And then sulfate. I'm going to look sulfate up on my sheet. I'm going to go SO4, and I'm going to see that it is 2-. And so then I need to put these together to balance those charges. Now 2+ balances out 2-, and so I get CuSO4. Nice and clean. But what if this was a copper 1 sulfate? It was copper 1 sulfate. Well, then this would be Cu plus 1. This would be SO4 2-. So I would need to bring 2 coppers to balance out that SO4. So this would be Cu 2 SO4. So this is where this can get confusing. Notice, this right here, this was my copper 1 sulfate, but this one right here was my copper 2 sulfate. So we need to keep track of these ions and make sure that we're assigning the Roman numerals to our cations. What if I have magnesium bromide? Well, magnesium, Mg 2+, bromide, that's Br-. So I can put those together, Mg Br2. So that's our basic formula for writing ionic formulas and writing ionic names. So let's go ahead and let's start practicing that.